Morning everyone, and welcome to our option on energy. Just let me introduce to you how we're going to be doing these lessons here. We're going to start off each lesson here by looking at a set of slides. These slides were prepared by Mr. Eastwood, who teaches at Richmond Secondary. We're going to use these slides here as a quick introduction to some of the key ideas that we're going to see in this lesson. After we go through these slides here, we're going to have a look at our textbook notes for a little bit more information, a little bit more detailed expansions on some of these themes, as well as practice through some questions. So without further ado here, let's start off. This is section 1 in option C on energy sources. We're going to start off here looking, as we do with energy sources, we're going to define energy source as something that's useful if it's able to release energy at a reasonable rate. So we know as an energy source is supposed to be a producer, as a provider of energy, but we're going to learn in this section here is it has to be released at a reasonable rate because it needs to be quick enough to be able to meet all your energy requirements at the time, but it also has to be slow enough so that it can be worked with safely. So one key feature in this section here is, again, this definition here of a useful energy source. You can think through what are some typical everyday useful energy sources. We do, like, for example, hydroelectricity. We do fossil fuel burning in our automobiles, things like that. So those ones somehow are able to harness the energy. We're going to see ultimate source of energy does come from the sun later on in this option here. But pretty much here, whichever energy source that you come up with, make sure that it does is able to release it at a reasonable rate, not too fast, not too slow. And another key feature we're going to see later on is the minimal pollution. So what are some factors that would affect this rate here? If, for example, in the fossil fuel example, we need to actually burn these sort of high energy, high density molecules and actually be able to burn them at a combustions are typically really quickly, but be able to design our engines so that they can capture these combustions, control the combustions to burn at a certain rate. And it's actually going to be able to release energy to the pistons in our car to actually run our cars. You see there's a lot of engineering aspects to that as well. That would specifically be an energy source here. Burning is a great example, but also we need to think about those factors affecting reaction rate. What's the temperature at the fuel? What's the state of the fuel, solid, liquid? What's the pressure that we're under? Some of those features that we learned back in our kinetics chapter. Again, a nice feature of a useful energy source, we do want to always be environmentally conscious. So if I have an energy source that produces minimal pollution, it's also a good thing here. Back to that car example, when we do burn fuels, typically complete combustions release carbon dioxides and water into the atmosphere. Yes, although CO2 and water are common greenhouse gases that are just naturally produced, there is an ongoing concern of perhaps some of these extra anthropomorphic sources that we toss into the atmosphere are actually causing extra pollutants in the atmosphere. So here's just a generic question here. When we talk about a useful energy source, releasing things at a reasonable rate and also producing minimal energy, which is a better energy source? If we consider like a AAA battery versus a voltaic cell here, what you're going to see in this chapter here is there's no like one thing that's always good. There's always pros and cons of either. For example, in the case of a AAA battery, we play around with the states of matter, right? We don't leave the electrolytes as liquid in case you want to orient the AAA battery like horizontally, vertically. I don't want that to affect how the electrolyte actually interacts with the electrodes. So they typically make AAA batteries out of a moist paste material here. We still have our anode and cathode like the voltaic cell, but typically we've engineered it in such a way that although we're going to see later on in the section, there's going to be some internal resistance as it travels through the battery. It is able to store a lot of chemical energy. It's not in use until you actually complete the circuit, so that has advantages in that sense. A voltaic cell that sort of is mimicked off of voltaic cell, we had the limitations of our electrolyte was just using the solvent in water. If you can keep the orientation always standing up, that's perfectly fine. Voltaic cells tend to run out very quickly, so although we do standard state, we want to do everything at 1 molar. If I can't actually contain a lot of chemicals inside the voltaic cell, that battery that we generate will actually die out quite quickly. So that's what it takes to be a useful energy source. It has to be able to release energy at a reasonable rate, as well as, if we can, produce minimal pollution. The second key idea that we're going to introduce here is the notion, although we do have energy conservation, the total energy that the universe started with is always going to be the same. We're going to learn in this section here, in fact, the quality of the energy is constantly being degraded. So what's happening here is although the total number, the total joules that we have inside our universe is always a fixed number, because energy, every time we do an energy transformation, there's always some heat inevitably lost to the surroundings. The quality of our energy is actually being degraded. So the focus here is not on quantity of energy. We're going to focus more so on the quality of energy. We start off from energy being concentrated, nice and useful, nice and good as energy source here, and gradually with every transformation that I make, although the total amount of energy is conserved, if you consider some of that heat that actually gets dispersed to the surroundings, that heat there is no longer available for use, so therefore the quality of itself actually matters. So keep that in mind here. Yes, we have energy conservation overall. That actually paints a picture in the first law of thermodynamics. You can't win. You can't end up running a reaction and end up getting more energy. And in fact, in the second law of thermodynamics, this is what this quality of energy conversation is talking about. In fact, usually when you run these reactions, usually we're always at a loss. Usually when some of the energy sort of escapes during your transformation, that energy is no longer available for use, and we can't use that in the same way we do concentrated energy sources. As we look at energy sources here, we can categorize them as either renewable or non-renewable sources. Right now, we do rely very heavily on non-renewable sources. So let's start off with some examples first. What are some examples of non-renewable sources? So to qualify here, to be non-renewable, these are things that, sure, they were maybe formed, if you rewind the clock here, maybe millions and millions of years ago. It took many millions of years for you to actually get these non-renewable sources. We're using them up really quickly. Think about the fossil fuels, think about oil, petroleum products, gasoline products that we're going to be introducing in the next section here. Those are called non-renewable sources because they provide really quality energy. They are really high energy dense molecules. We'll even be able to calculate how much energy that they release. But unfortunately, because we're having to run so many automobiles and transport devices, we're going to be using up these fossil fuel sources much quicker than they can be replenished over the millions and millions of years. So any fossil fuels and gasolines are examples of non-renewable sources. In contrast, let's think about some renewable sources as well. So renewable sources here, as it sounds like here, it does also talk about a source of energy, but because it's renewable, doesn't mean that it's automatically regenerated, but within our sort of time span, within, if I use it up in a week, I can probably get it back in a week or so. That's something I would consider as renewable. So for example, hydroelectricity. Turns out we're going to see in our section later on, rainwater actually holds all the potential energy that water power would have. It's just that rainwater, it drops so steadily and drops so slowly that it doesn't generate at a reasonable rate, so therefore it's not a useful energy source. If I collect up all that rainwater, I build a dam, I basically control how quickly the water actually flows out. We can actually cause the water to flow out much quicker at higher pressures. That's something more of a renewable source here. As I generate that hydroelectricity, we then just wait for the rainwater to replenish our dams, and therefore within a short time span, we have used the energy, and we also been able to replenish that really quickly. So that's our third big idea in this section here. A renewable energy source is something that's naturally replenished on a time scale that's useful. Again, it doesn't mean necessarily automatic, but it is fairly quickly how quickly it can be regenerated. Again, back to your question, how can we rely so heavily on non-renewable energy sources at this moment here is because they're good. They're very useful. It's just that again, they're going to have some problems with environmental considerations, but also the bigger problem here is we cannot regenerate them as quickly as we would like. Just going to show you a few quick slides here on C2, on fossil fuels as well, as we look at this as an example of a non-renewable source, why we rely on these so heavily. We're going to start off just with a generic term here, fossil fuels. So fossil fuels here, these contain eventually our gasolines, our oil, our diesel, different petroleum products here. This fossil fuel is the umbrella term for all of those. And they're saying the reason why these are non-renewable is because it took the reduction of biological compounds. Think about living creatures here that lived millions and millions of years ago. When they died off, they got buried, whether they got buried on land or in the ocean. They got trapped under there for high pressures, high temperatures for a long, long time. And what ended up happening was those living molecules, those biological molecules that are inorganic, we learned it contains carbon, hydrogen, nitrogen, sulfurs, and oxygens. It tends to start getting reduced. We tend to lose the the Ns, the sulfurs, the oxygens more quickly, and eventually what's going to happen is those what would have been living molecules are gradually going to lose those products and eventually become hydrocarbons. Eventually we can harness them for our fuels. So just two last slides here. We're going to look primarily here at coal as well as petroleum products. They will generally ask you how coal is formed here, so they have a nice little comic strip here. Coal, imagine we have a swampy environment here. We had giant plants in the swamps. When they died out, they basically get buried under a layer of dirt, maybe over many millions of years. Even water covers over the area. Eventually that applies a really high pressure on these dead plants. There's a lot of reduction of those biological compounds, and eventually we're going to have a deposit of coal, which is high energy, but this one here takes millions and millions of years. This one here focuses on starting off with land plants. We're going to compare that to a comic strip here on petroleum products, also captured under a fossil fuel umbrella. In this case here, petroleum, you want to just note, in this case here, we're looking mainly at oceanic creatures, so not plant-like materials. These are sea plants or as well as sea creatures. As they get buried on the ocean floor, same idea, they get covered over, in this case here, with sand and silt, and over millions and millions a year, with enormous heat, enormous pressure over long periods of time, they eventually get refined into the oil and gas that we use nowadays. Typical oil refineries nowadays, they have to actually dig deep, whether it's ocean drilling or even land drilling. They're going to basically take up all these oil and gas deposits from the ocean and actually be able to harness that as a non-renewable energy source. So those are our slides for today here. We're going to switch over now and we're going to take a look at our textbook and we're going to try to practice through a question or two. All right, so now that we've taken a quick overview look at some of the major ideas, let's just have a look at C1 again on energy sources. These notes here were compiled from our 3 IB textbooks, from the Pearson, from the Oxford, as well as from the Cambridge textbooks. And we're just going to take a look a little more detail, maybe flesh out some of these concepts a little bit more. A lot of it was already introduced to you in that PowerPoint presentation. So we're going to start off here looking again at C1 and the earlier parts of C2. C1 is on energy sources, so it's a provider of energy. We're going to start off with the qualitative definition here. What is energy? Turns out energy is something that's fairly hard to define. We're going to use the capacity here. Energy is something that has the ability to do work. From your physics, you've probably learned work is also very strictly defined here. In physics, we say work is defined as something that can apply a force over distance. Things that have energy can do stuff. Things that have energy can cause transformations, whereas things that have low energy, we had said before, they're more stable. There's not a lot that can go wrong. So we look at a couple energy sources here from very ancient days here. We had wood fire burning that generated all the heat and the light that we needed, to nowadays we talk a lot of interest about nuclear power. We're going to do a section later on solar cells, or what are called photovoltaics. So solar panels, how do they harness the heat energy and actually running our everyday activities. I mentioned here we have, yes, the first law of thermodynamics. So this is the first law. First law of thermodynamics basically says energy is conserved. The E in is equal to E out. You can't create it, you can't destroy it. Whatever the energy starts off with, that's the energy that you end off with. I mentioned that sort of starts off our depressing picture here is you can't win. You can't provide some transformation that you put in less energy and somehow you get more energy off of it. So it's saying that the total amount stays fixed. And in fact, the second law here, like we said, is a little more depressing. The second law, because with any energy transformation, energy is always going to be dissipating and sort of spreading out through the environment, the quality of it is constantly being degraded as well. So in this case here is you always lose. So this section here introduces, yes, we know energy conservation. Yes, we know the quantity. The number of it never changes. Let's do an example here. Let's say I have like gasoline inside my car engine. Let's say the gasoline, it's a non-renewable source like we just saw. Let's say I'm going to burn 100 joules worth of energy provided from the gasoline. The total number is going to be fixed. That 100 is always going to stay fixed there. Some of it is going to be used to actually run. So in this case here, some of it is to transfer to kinetic energy for my car. I'm hoping a lot of it, let's say 60 joules. Some of it is lost to heat energy, just heat that's escaping your engine. Maybe that's, I'm making up these numbers here, 20 joules. Some of it as you burn your fuel here, some of it's lost to sound energy. Maybe that's, 10 joules. I can totally make up these numbers. What I want to show you here is with all the different sort of forms of energy, although energy conservation is still true, although if I burn 100 joules, although the total amounts of all these types of energy, I just put the dot 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 because there could be many other forms, although the total amount of energy is formed, how much was actually useful was actually just some fraction. In physics, you do an efficiency here. Obviously, we want to design engines that are more efficient. But so far, we're going to just say, well, some of the heat is actually lost away. Even though the total number is 100, the quality of the energy is constantly being degraded. So just keep those two terms in mind here. Although the quantity is conserved, the big idea here is the quality is steadily being degraded this way as energy gets spread out and lost to the environment. It's no longer available for useful work. So as I just mentioned here, we have this efficiency notion here. I want to figure out how much useful output energy. Based on my numbers here, I was able to get 60 joules worth of, let's say, kinetic energy here for my car, divided by 100 joules of gasoline that I burned. That's going to be unitless. So you get times 100. So currently my efficiency is 60%. Sometimes they use eta for efficiency. It's like a long N. But basically it's trying to track here how quickly has your energy degraded away. You can think about here, why is there this sort of typical efficiency? We see actually some efficiencies from power plants here. A gas power plant here, when it tries to convert the gas to some more useful gasolines and other crude materials here, the efficiencies tend to be fairly low. 45% oil, downwards of coal, 35% here. You can think about what the power stations are trying to do. They're trying to take a random motion from the gas, basically particles that are going every which way, colliding randomly, and we basically want to engineer some systems, engineer some turbines that all the particles then go in the same direction. Maybe it can then spin a turbine for us. We're having to coordinate all these particles here. There's going to be a lot of losses along the way. In this section here, we're going to introduce some of our key vocabulary here. We are interested in energy sources here, so a generic term here for an energy source is a fuel. It's a fuel that releases energy. We're going to have two main types of fuel. First type of fuel here is called a chemical fuel, or what's referred to as fossil fuel. These pertain to your gasolines, oil products here. This is doing chemistry to end up releasing off energy, like burning, combustion style reactions. We will do a section later on nuclear power plants as well, although there is a little bit of nuclear chemistry involved as well. That typically generates energy in a different fashion. That typically causes changes in the actual nucleus itself. So starting off here with the chemical form, the fossil fuel form. Fossil fuels, the reason why they're such heavily used nowadays here and there's such high quality energy is they are a chemical store of solar energy. In fact, our ultimate energy source I mentioned before, it comes from the sun. These were plants millions of years ago. They photosynthesized, they created high energy sugar molecules. They had since died off. They got buried under layers and layers of soot and silt and materials. And basically over that reduction, we end up generating these fossil fuels, these oil deposits that we dig out of the ground. Currently, oil is our greatest provider of energy to the world economy, although we're keeping in mind here it is a finite resource. That's why there's a constant push here, seeing if we can transition to relying more so on more renewable sources versus things that are more finite. Nuclear fuels instead here, it deals with the nucleus. So again, what we're going to see is those alpha, beta, gamma radiation. We're going to generalize that into sort of fusion and fission style reactions. As the nuclei itself adopts a more stable or different arrangement, it's going to end up releasing off energy. Here's our first two sort of calculation worthy terms here. One is a notion here called energy density, and the other is a notion called specific energy. Whenever I see the term specific, like specific heat, I always think in terms of mass, so maybe that's going to be helpful for you as a memory aid. But in some sense here, both of these terms here, if I give you the specific energy or the energy density of something, what I'm defining for you is how much energy can that field give you, specific says, per kilogram worth of material. And you see the units here. Typically, if I'm burning kilograms worth of chemical, I typically will have in the orders of megajoules, so millions of joules. Specific energy is something nice to think about. So if I'm going camping and I'm carrying my propane tank and whatnot, this is going to tell me basically how heavy of a gasoline tank I'm going to carry, because per grams of my propane, I'm going to figure out how many joules that grams can produce for me. We can also get an equivalent here, energy density. For energy density, what it is it's also trying to give for you how much energy is being released from the field, but this time it's a density, so it's released divided by volume. So based on the density of the field itself, maybe 10 grams of this material, maybe it takes 2 canisters worth of volume, maybe 10 grams of another fuel, maybe it takes 4 canisters of volume. I basically figure out how much energy is released per canister or per volume of fuel. And in fact, we can just switch over to a quick calculation here, just looking at the units here. If we started off with, say, specific energy, so specific energy, I see that that's in units megajoules per kilogram. If I wanted to ever convert it to energy density, or vice versa, energy density is supposed to have the units here megajoules per liter. What we're going to have to do is you're going to basically, well, I need to cancel kilograms and I need to basically divide by liters. Have we seen this conversion before? A conversion between mass and volume, well, this is just straight density. So the actual density of the chemical itself, I might need to look up that value. You can always Google them, whatever. But if you have the density, you can actually make sure we would typically go grams per milliliters, make sure it's in units kilograms per liter, and you can convert between the two of them. So towards the end, I'm going to show you a quick calculation, how we can utilize that. Let's just skip our way through the last little bit here. So combustion enthalpy, so we're going to see this on table number 13. We do need a data booklet for this section here. Table 13 tells you per mole of a chemical that I burn, here's how much kilojoules that it releases. That doesn't necessarily tell the whole story because depending on the density of the fuel, depending on how heavy and how packed it is, maybe the specific energy or the energy density may be actually different. So while I have a gasoline that might have a very high combustion enthalpy, every time you burn a mole, it's going to release tons and tons of energy. But maybe when you factor in density, when you factor in you're having to carry it and store it and things like that, maybe it's a little bit less attractive of a fuel. We talked about here, our key term here is to be a useful energy source. We are our key ideas here. It has to be able to generate at a suitable rate. And the plus side here is if it produces minimal pollution. It's nicer if it's also cheap and plentiful, if it's accessible where I actually need it, if I don't need to transport it over long distances. So here are some examples of things that are not useful. Rainwater, like I said, rainwater is up in the clouds here. It's stored a lot of gravitational energy, right? It has a lot of capacity, a lot of room to actually fall. And yet when those rain particles actually start dropping, first thing, the rain particles here are very tiny. They're going to drop way too slowly to actually generate enough energy for me. So in that case there, it releases energy too slowly. It's not useful. Nuclear reactors have the opposite problem. When I run a fusion reaction, we're always worried about it going out of control, this chain reaction, and it sort of basically one thing triggering another reaction here. I'm worried of it actually being too quickly to actually be used safely. So in both cases here, we want a useful source that's not too fast, not too slow. We also want the added feature, if I can rely more heavily on renewable sources that can be replenished or replaced faster than we're using it up. Unlike the coal that takes millions and millions of years to form, maybe I just grow another tree so I have more wood to burn. Maybe I set up ocean reservoirs and ocean dams or so, and I harness that hydroelectricity. That can also be an advantage. So they make sure you can give me some examples of these alternatives here. We can do wind as kinetic energy, hydropower from wave energy, tidal energy. Bioenergy is using like diesel, using vegetable oils as fuels, geothermal, harnessing the heat from the earth. And all these ones here are typically going to be more environmental than releasing CO2 over such short periods of time. CO2 is naturally being created in our environment, but what we're worried about here is our fuels are generating way more CO2 than there would normally be. We're going to look in more detail in the next lesson about fossil fuels in general. Fossil fuels is an umbrella term for all the coal, crude oil, petroleum products that we're talking about. Fossil fuels here are a non-renewable energy source. We do rely on them heavily because they provide good, high-quality energy, things that have high specific energy and high energy density, but we're just keeping in the back of your mind, we're using them way quicker than the millions and millions of years that it took to form. So sometimes they refer to fossil fuels here as sunshine in solid, liquid, and gas, but these had to be formed millions of years ago. We talked about here, with the comic strip here, we talked about coal and petroleum. For coal, we basically looked at decomposition of plant and animal matter over many millions of years. What we're going to see is the living particles, typically organic molecules are our chons, so made out of carbons, hydrogens, oxygens, nitrogens, and sulfurs. Over the millions of years, over the reduction of these compounds here, we tend to release and tend to lose the oxygen and the nitrogen and sulfurs much quicker than carbons and hydrogens, and we end up with a bunch of these hydrocarbons. Unfortunately, when we actually dig this out in the earth, it actually comes out as a crude oil. We're going to talk about in the next lesson how do we actually distill to actually separate these ones so they're useful for our different uses. But eventually we just harness all this oil here. With every process that I sort of run this through, I basically want to increase the amount of carbon. And basically sometimes I can use peat just directly. If I sort of run it through a chemical reaction and I increase the amount of carbon source here, eventually we get to coal, which is about 80-90% carbon by mass. It talks about it coming from sedimentary rock as well. And by combusting that coal here, we can release all that high quality energy in the bonds to actually release it in the environment. Petroleum here, we mentioned from the comic strip here. Specifically, we're looking at decomposition. I'm going to make a note here. Decomp of more so oceanic creatures, oceanic animals, oceanic plants as well. Sort of same idea here though, millions of years, high pressure, high temperature for it to actually reduce enough. So we're going to end off this lesson here. We talked about a useful energy source. We introduced these two terms so far, specific energy, energy density. Let me just show you an example. You'll see more of these examples on the worksheet that I'm going to provide for you here. Let's start off with a fuel here called hexane. So we know from our organic chapter here, this is C4H14. We're going to find that this one here has a large enough molecule. The London forces are actually a little bit bigger. So hexane here is actually a liquid under our regular conditions. Liquids are good because they're easy to store and they're easy to transport. This is a good idea. I'm going to give you that the actual density, so not energy density, this is just the sort of matter density here. You can just Google this or look up this number here, is 0.6548 grams per milliliter. In this case here, you can convert the units over. You can try it out for yourself. That would be equivalent to a kilogram per liter. Right? What we're going to also do here is rely on section 13. Section 13 here has a bunch of heats of combustion. And what we're going to do is we're going to look at the enthalpy of combustion for this chemical. And it says for us here, the enthalpy of combustion, when you burn 1 mole of this chemical, all heats of combustion are exo. They release energy. That's a good thing for me. It releases off 4163 kilojoules per mole. It releases thousands and thousands, but unfortunately this one here is based on moles and also therefore is based on sort of burning this mole here. So let's start off here. If you remember, for a burning reaction, we had C6H14. For an actual heat of combustion, we had that pesky little 1 mole. I want to quote all these ones here as per mole of reaction, so every time I run the statement once, how much energy is released. So burning requires reaction with oxygen. We assume complete combustion. If it was incomplete, it produces carbons and carbon monoxides, a dirtier flame. In balancing this here, all the carbon ends up in the CO2, all the hydrogen ends up in the water. This one here, unfortunately, we're left with the odd fraction, but that's fine. If I'm able to burn that reaction, every time I run this statement once, it ends up releasing off 4,000 kilojoules of energy. Let's also do the molar mass just for convenience sake here. The molar mass of my hexane, just add up 6 carbons and 14 hydrogens, I'm getting 86.20. So here's what I can do. I can start off with the heat of combustion and trying to calculate, reword it in terms of energy density, specific energy. I'm going to start off with 4163 kilojoules per mole. I know that it's actually being released, so I can just say in words, this is the amount of energy released. So you can keep that as a positive number. Let's do a conversion over here. If I want to get rid of that, if I want to get rid of the moles here, I go, well, my molar mass was 86.20 grams per mole. That cancels out. Then I get kilojoules per gram. I'm going to just convert the units just to put me back in the right units for sort of specific energy and energy density. I'm going to actually have it in megajoules instead. For megajoules here, we're going to go 1,000 kilojoules. So that kilojoules here will cancel the kilojoules that we had from our heat of combustion. And I also want to convert the mass term here. I have grams. Usually when I do specific energy, it's in kilograms. So I'm also going to factor out 1,000 grams per 1 kilogram. The gram cancels gram. Type in all the numbers over. And what I got previously, keep track of your sig figs here, I got 48.29. What the units that we have is we now have it expressed in terms of megajoules on top per kilogram. Something that's megajoules per kilogram is the energy released per mass. And that reminds me here, oh, this one here is actually specific energy. So we've been able to take our combustion enthalpy from grade 11 and actually convert it over to our new term, specific energy. Remember, I just talked about if you know the density of the actual chemical, this 0.6548 hasn't come in yet. If you know the real matter density, you can convert from one to the other. So let's say the question was calculate the energy density. So calculate I just look in terms of units here. Energy density here should be megajoules per liter. Let's take this one here, which was, we just calculated 48.29 megajoules per kilogram. I'm going to need to divide by the actual density. The actual density says when there's a 0.6545 with the kilograms, 0.6548 with the kilograms, that's equivalent to a liter. So just punching it through the density, double check my numbers, I get 31.62 megajoules per liter. So we've taken our heat of combustion that we were very familiar, that was useful for a balanced equation because it's always per mole, but this time we're actually thinking about more generic and qualitative here. As a fuel, every kilogram worth of this liquid is going to provide for me 48 megajoules. If I'm considering the amount of room it takes to store this one here, every liter of fuel only produces for me 31 megajoules. So this introduces the element of the transport and the storage as well, not just, oh, this has a high heat of combustion, of course, burn this fuel. So that finishes off for this lesson here. Make sure you practice a few questions through our C1 section here, and we'll come back tomorrow and take a look more at fossil fuels. Thanks, guys.